All right. Of course, I'm also grateful to the organizers, but would also like to thank all of you for actually sticking around for the last session. I think that's impressive. I'm sure you're pretty tired, but I'll keep this simple. So I'm Rahman Amanullah, and I will say a few words about reddening. I'll be interested to hear what you think about it as well. So why should we care about reddening? Well, it depends on what hat you put on. You could put on your supernova hat, and you can understand that dust in the supernova environment could tell you something about the supernova reaction. You could put on the dust hat. I did not realize that there was such a hat, but you could actually be interested in dust itself, what's going on. And supernovae are excellent lights. Okay? We can use them as lamps in other galaxies, studying dust in other galaxies. Or you could put on your cosmology hat, of course. It's very important to know how to correctly report cosmology. And if you don't wear a hat, I can help you. So I'm going to start by putting on the cosmology hat. We've seen this quite a lot. This is the Betul sample. These are Hubble residuals you have here, but I'm only corrected for stretch. I have now a lighter shape. I'm not corrected for color, so you have a color here, and you have the corresponding distributions here. And you see this clear correlation. This is what is called the salt color. So for those of you that are not doing quantum cosmology, you can think of it basically as the deviation from the B minus B average of Tech-9 supernova, training of the sun. And you see this relation that you get between the two, and you try to minimize it for when you do cosmology. We saw a similar approach for the Type 2 supernovae. And all of this is fine, of course. Here you have the color distribution of the 740 supernovae, and here you have the magnitude residual distribution. The only point I want to make here is what you will get here will depend quite a lot on your sample. So you can see here that you have a fairly symmetric color distribution in this parameter, or a fairly symmetric Hubble residuals. Maybe there's a tail here, maybe these are your supernovae that are suffering from extinction. But this is the point, right? Most of us believe that what is in this mess is a combination of some intrinsic Hubble property, and we know there's dust in there. So that's what you have here. And if the two relations are different, well, then whatever you get out will depend on the fraction of the two here. So I want to compare this, for instance, for IPTF. So this is the Betul sample here, the JLA sample here before, and this is only Hubble residuals without color correction. And you can see that this is stretching further out on the faint end. And I have only included the PTF supernova here before we're getting into the Mancos bias. We don't have colors for PTF, but I would guess that this is reddening, this is extinction that we're seeing here. So clearly, if we would have color, we would probably get a different relation for this. Then, of course, people have tried in the past, several of you are in the room, to separate these two effects, trying to separate the intrinsic dispersion, the intrinsic color relation, and extinction in different ways. I've listed a few of the authors up here using either trying to estimate the color distribution or trying to use intrinsic features of the supernovae, like these two authors did. And what's interesting when you do this is that RV seems to be bumping up towards 3 when you do this. So you could say here, oh, well, what is pulling RV down is just the intrinsic color relation that is dominating when we do things like this. What we're actually seeing out there is standard RV, standard Milky Way dust. But then, of course, we have supernovae like this, 14J. What you're seeing here is the extinction law. It's not quite clear, but this is the color excess with respect to the V band that you have here, and here you have inverse wave migrants. If you're not used to this, I've also plotted the filters that this were taken in. You have the infrared filters here, and you go all the way to the UV here. You can see the standard RV3 law plotted here, and this is if you're letting RV float, you're getting something like RV 1.4. If you saw in the previous plot, out of this 740 supernovae, the dispersion was about 0.1 mag. And here we're measuring a color excess of 1.4. So this is clearly not something intrinsic to the supernovae. This is dust. This is dust where we're seeing, and we're seeing dust with a low RCP. I want to make one more point here, and that's that the best fit to this is actually a power law. But when we're fitting these standard derived Milky Way-like laws, like the Fitzpatrick 99 law that we used here, and pushing them down to these very low RV values, we're doing huge extrapolations because these things were derived in a Milky Way, not really suited to these things. It's also interesting to see that when you add this UV data, this is where you see most of the discrepancy really from the static Milky Way dust. You're also allowed to actually study the full reddening law, the full extinction law. So we often talk about RCV and what is the standard RCV and stuff, but the story is bigger than that, right? The story is not just RCV, the story is actually what does the extinction law look like. And a lot of people that are working on Milky Way dust are moving away from this and actually noticing that RCV is not the only description that you use. You need at least 2 parameters. Okay, so we have this, and we argue that this is actually extinction. You can also look at the interstellar features. You have clear sodium lines for this. You have calcium lines, and you also have this DIB here, 5780. And if you use the famous Phillips relation, and I'm of course referring to the Phillips relation where you can get the extinction from the 5780 DIB and nothing else, you get an AD over on 2, which is the same thing we're getting from colors. So this is extinction. This is nothing to do with supernova. This is strange dust, if you wish. All right, so I'm going to spend 2 slides on circumstellar dust. It's been discussed already. But this idea has been around for a while. There was a poster here at this conference by Takashi Nagao. It was sitting right there. But unfortunately, he had to leave a couple hours ago. He took the poster with him. So I hope you've already seen the poster. So the idea is very simple. If you have circumstellar dust, photons that scatter in the dust are not necessarily lost. They could be observed. And the effect of that is if you put in, for instance, LMC dust in there, you will get a steeper, whatever dust you put in there, you will get a steeper reddening law. And if you put LMC dust in there, you can get something that looks like RB1.4, for instance. And this is an intriguing idea in the past because people have been seeing these varying sodium lines, the sodium absorption lines at very good time. So obviously, there are supernovae 1A out there with circumstellar dust. I just briefly want to point at this again. Ariel showed this work earlier. This is from the Institute in Stockholm, looking at one of these things here. One of the supernova, 13GH, and this is the sodium D2. And he saw variation here. I want to spend a little bit more time. You can't really see this, but this is the actual variation that he's observing over time. So this is going from -9 days from maximum to plus 30 days. And this is the derived column density that goes down with time. And the solid line here, that is a very simple model that you get from a single dust shell, a single circumstellar dust shell at this radius here. This radius is too far away to affect the RV, and I'll get back to that in just a second. All right, the thing that I really wanted to point out here is that if you want to do this type of measurement, a lot of the varying certain region is seen is actually coming from later on. This is not this decrease in equivalent width. And the simplest interpretation for a decrease in equivalent width is it's actually ionization. And seeing something like this is great because if you're seeing variation in the ionizing phase, you can actually determine the distance of the circumstellar matter. And that is important if you want to interpret this as affecting the reddening law. And you can see a plot here, what you need to do. So typical radii that are interesting for circumstellar dust in order to actually affect the observed reddening law start about 10 to the 16 centimeter and go out to 10 to the 17 centimeter and so on. And if you want to catch this during the ionization phase, you really have to get your observations early. So I just want to make this point that these are the things that could affect the reddening law. And I can show you one more slide on circumstellar dust. A lot of people looked into this. This is from a paper that Ariel and I wrote a few years ago. I just mentioned that the effect of the reddening law for circumstellar dust comes from the scattered photons. And this the scattered photons are coming from the supernova itself, of course. So it's basically a short light echo, but the light echo is at the same time scale as the light curve. These three curves are showing three different circumstellar dust shells in different radii. This is 10 to the 16 centimeter, 10 to the 17 centimeters, and 10 to the 18 centimeters. And the black curve is the original supernova you would observe. And the point I want to make here is once we get to 10 to the 18 centimeters, you're back at the original curve. It does not affect the curve at all. And that will also be true for the colors. So if you take 14J, for instance, and you study the color excess over time, before I showed you a compressed version of this, what you see are these figures here. So this is, again, infrared going all the way to the UV. And you can see that for 14J, you see the solid lines here being what you would expect without circumstellar dust. So you don't have this effect at all. And you can see that the data is basically following the expected color excess almost perfectly for 14J. So the origin of the extinction of 14J, well, we don't have any evidence for it being circumstellar. This is something in discovery media. All right, so I wanted to mention one more thing here, and that we also went back and tried to look for the re-emission. If there is circumstellar dust there, it would be heated by the supernova, and you should expect to see that longer wavelength. We did not see anything. We looked at other supernova, we did not see it either in any. So perhaps circumstellar dust as the main explanation for these low RCD values is not the right one. And a lot of people have made the same claim in the last few years. So at the end of the talk, I want to say something about the diversity. This is another study we did. So we followed 7 type 1a supernovae with HST linear UV. You have the lowest galaxies here. If you look at the 4 most reddened supernovae, these are the 2 reddening laws that you see. What you see here is standard Milky Way dust, so RV around 3. You see that 3 of these are following this quite well, while the 14J is quite an outlier. Again, the fact that it doesn't fit the curve perfectly here comes from this extrapolation I mentioned earlier. We've also studied these supernovae very carefully. We took high resolution spectra of them, we looked for time evolution and so on, and we didn't find any. My point I want to make here is that one of these has EBV of 1. They are highly reddened, and they show standard Milky Way reddening. This guy is highly reddened. It shows non-standard Milky Way, or low R sub B if you want, if you rather prefer that language. And none of them show any signs of the circumstellar dust. Again, in the UV here, so this is AB or A lambda, so I'm calling something slightly different. In the UV here, you see a striking difference between the extinction law. And the point I want to make is that this is a great place to study reddening laws. Here, you have the most discrepancies. This is where you're most sensitive. So UV is great, but UV is also great for observing low reddened supernovae. This is EBV, R sub B. This is showing you the uncertainties of the 2 parameters. The gray is the uncertainties when you're trying to fit for 12 CG. When you try to fit the reddening law to only near infrared and optical data, the blue is the uncertainty when you add in near UV data. So it's just strings. So using UV is great for the precision of low reddened supernovae and also to study the entire reddening law. I'm going to end with this plot. This is my last plot. This is adding the supernovae that we have to the literature values, mainly from the CSP, but also other literature values. We also added some quasars here. The color bugs are the HST supernovae. And you can see at high EBV, we see both low and high RCP, and we sort of see the similar thing at low values of EBV. And again, because we're adding going all the way out to the UV, we can actually have relatively small error bars here for the relative small reddening. One point I just added this plot, constant AB, and that's to avoid confusion. Of course, in a real survey, we're not color limited. We're not selecting on color. We're selecting on magnitude. So this is showing you the constant extinction. The point I want to make is it's much more difficult with all the biases that we have against faint supernovae and so on. It's much more difficult to find highly reddened supernovae with high RCPs. So there's probably a selection effect in our samples. And I want to end on that note. When we talk about this business and we want to fit the average RCP we have to be quite careful in how the supernovae were discovered in the first place. Great people, we've heard of this, great people are doing this, they're really also worried about the supernova did not find. I'm not sure that us that are looking at reddening loss have been equally careful, but the point I want to make is that we probably should be, because we might be missing highly extincted supernovae with high RCD. Otherwise, it's just what I just said. We see a diversity in RCD stretching all the way from down to RV1.4 to standard Milky Way of individual supernovae, and we see it for highly reddened supernovae in both these ranges. CS dust, well, maybe not the main explanation, at least I don't think so. This is probably dust in the galaxies. Adding UV data is really, really great if you want to do this, and I think we need to do it to probe the full distribution of dust properties out there. All right, thanks. Why are you sitting in the back, Sarah? It would be a lot easier for you.
Comment and question. The comment is, I think, I agree with you. I don't think surface color dust is the answer. And though maybe Alejandro's talking, maybe pointed the other way, so we have to figure this out. I think one of the pieces of evidence for that is the couple of supernovae where we have direct light echo detections. So 2006X and 14J, you can actually see the light echo. And from the light echo, you can estimate where a dust sheet is. And there are many parsecs away, tens of parsecs away from the supernova. And if you, it doesn't prove that that is the dust sheet that is responsible for most of the extinction, but it looks like there's enough dust to do that. So the simplest explanation would be that is also the dust sheet that is extinguishing the direct line of sight of the supernova. And that's where the rear dust is. And so I think in those cases, it's not so hard. My question for you is, do you think that selection effect explanation could explain why we don't see any RV of 5 supernovae? Or is it something else?
I don't know. At some point you would see them as very faint supernovae, right? Even though the dust is very gray. But I don't know. I haven't actually looked at the surface. Very few surfaces are really many magnitudes below peak mag, which you need to be if you want to find RV5. I don't know the answer, but I'm not ruling out that it's out there. If we see dust with high RCD anywhere else, there should be a supernova exploding behind it at some point as well, right?
Any others? Regarding the supernovae that you showed with HST data and different RBs or different extinction laws, do you have information about the presence or absence of suddenly anomalies?
Yes, so they, we read it in the paper, I don't remember exactly, but they both FLCU and 14J that I showed have sodium D, and we quantified the equivalent with it also in the paper for 12CU. I don't remember from the top of my head what you, for instance, when you use this non-stimulation, what you get in terms of AE for it, but it is in the paper. Yeah.
I would like to repeat what I said this morning. We should pay attention to the 22 supernovae because they also indicate low RCDs.
Right. And we saw this paper by Max and others. It's interesting. So that might suggest that it's not weird dust from circumstellar material at, say, 10 parsecs or so.
Any other questions?
So, I think in the paper that Chris wrote, there's sort of an indication that maybe the low RCD might go with high velocity gradient, high velocity supernovae. What do you think about that?
Right. Out of our sample of 2 supernovae with low RCD, we see the same thing. So again, I'm flipping back and forth, but that would suggest that they're going off, those supernovae going off in an environment where the dust has that property. I don't believe it's a property of the supernova that I was suggested in the past, because I think, for instance, Gordon J clearly shows that the dust is far away from the supernova. So I don't think it's an intrinsic property of the supernova, but perhaps it's telling us something about the environment.
Since the sample of light curves from Swift is now partly average, can you do the same kind of stuff with Swift?
So you can, so the question was if you can do it with Swift. So you can, and people have looked at reddening law, the Peters, as I like to call them, Peter Brown and Peter Milne, have looked at similar things. With Swift, of course, I think the only really usable filter is UVM2, because the other have way too much red tail for these things. The other thing with Swift, and why I prefer HST, is you cannot go out to the Hubble field with Swift. And with HST, you could just do what I showed here in the Hubble field. I think that's much more usable, because then you can do this for supernova and actually end up with the Hubble diagram. And you also have the independent distance. You can look at magnitude residuals and get an estimate from that. So, but it's certainly useful to use with Swift as well.
Okay, let's thank Rahman again.